Dear students, welcome to EPG Pathshala. I am Dr. Rajkishore Sharma, an Associate Professor from Chemistry Department, University of Delhi. Today we are going to discuss about the module Instrumentation of Energy Dispersive X-ray Spectroscopy. This is under the paper of Surface Analytical Techniques 2. After having knowledge of what exactly this energy dispersive X-ray spectroscopy is, we will discuss about the instrumentation of energy dispersive X-ray spectroscopy. As we all know, this analytical technique is based on a surface phenomena and it deals with the composition of a sample. It is interesting to know the process through which this is possible. What are the all instruments that deal with it? What are the components of the EDAX instrument? How does the component function? What type of materials can be analyzed? And many more questions must be coming to your mind. To answer all these questions, which you might be coming across, will be covered in the upcoming slides. So here we'll start. The topic that we are going to cover in this module, the component of EDAX system, the excitation source, the X-ray detector, the silicon drift detector, pulse processor and the computer display. So the first is the component of EDAX. Students, basically there are four components of EDAX. Number one, the excitation source, or it is known as electron beam or the X-ray beam. It is the major component of EDAX machine. It is an essential component to start or to initiate the measurement process. The second is the X-ray detector. It detects the X-rays, those are ejected from the sample. The third is pulse processor. It is used in measuring the signals emitted from the sample. And the fourth is the analyzer. It analyzes the signals and gives us the final results. Before going into instrumentation part of the EDAX analysis, we need to understand how EDAX works. Images corresponding to the electron microscopic radiations and the transitions in an atom. The slide shows the electron microscopy background. When beam of incoming electron hits a specimen, it gives rise to various signals. For example, secondary electrons we call SE, backscattered electrons BSE, OJ electrons. It gives cathodoluminescence in the form of light, and it also emits X-rays. So in electron microscopy, we got particular kind of signal, we trace it, detect it, and modulate the surface morphology. In case of EDAX, when a radiation or beam hits an atom, it ejects inner shell electrons to vacuum or to higher levels. In this process, electron from the upper shell, another electron from the upper shell takes the position of the hole created by the ejection of first electron. While this returns to a lower state, it emits X-rays. We record the energy of the X-ray, corresponding energy, and relate it to the different levels like energy for K alpha, L alpha or K beta. So this is the mechanistic aspect of EDAX, how EDAX works. EDAX systems are most commonly found on scanning electron microscopes and transmission electron microscopes. The EDAX X-ray detector measures the relative abundance of emitted X-rays versus their energy. The detector is typically lithium drifted silicon. It is a solid state device. When an incident X-ray strikes the detector, it creates a charge pulse that is proportional to the energy of X-ray. The signal is then sent to a multi-channel analyzer where the pulses are sorted by voltage. The energy, as determined from the voltage measurement for each incident X-ray, is sent to a computer for display and further data evaluation. The spectrum of X-ray energy versus count is evaluated to determine the elemental composition of the sample volume. This is the schematic illustration of EDAX spectroscopy instrumentation showing the basic components. Interaction of an electron beam with a sample target produces a variety of emissions, including X-rays, and an energy dispersive detector, that is EDS, is used to separate the characteristic X-rays of different elements into an energy spectrum, and EDS system software is used to analyze the energy spectrum in order to determine the abundance of specific elements. EDS can be used to find the chemical composition of materials down to a spot size of a few microns and to create element composition map over a much broader raster area. Together, these capabilities provide fundamental compositional information for a wide variety of materials. Now we will discuss how EDX works. EDS systems are typically integrated into either an SEM or EPMA instrument. EDS system includes a sensitive X-ray detector, a liquid nitrogen devar for cooling, and a software to collect and analyze energy spectra. The detector is mounted in the sample chamber of the main instrument at the end of a long arm, which is itself cooled by liquid nitrogen. The most common detectors are made up of silicon lithium crystal that operates at low voltages to improve sensitivity. But recent advances in detector technology makes available so-called silicon drift detector that operate at higher count rate without liquid nitrogen cooling. An EDS detector contains a crystal that absorbs the energy of incoming X-rays by the process of ionization. It yields free electrons in the crystal that become conductive and produce an electrical charge bias. The X-ray absorption thus converts the energy of individual X-rays into electrical voltages of proportional size. The electrical pulses corresponds to the characteristic X-rays of the element. The excitation source. It includes an electron beam or X-ray beam, which are electromagnetic radiation and are very energetic rays. It is used in electron microscopes, transmission electron microscopes, scanning electron microscope, etc. You can easily see diagram shown in the slide above, which is a schematic representation. Now, how X-rays are being produced? This is an important question. These X-rays are produced, high-speed electrons hit the metal target. It requires the X-ray tube, and the X-ray tube requires a source of the electron. It also requires some means to accelerate the electron and a target to stop the high-speed electrons. Further, we will see that the electron that comes in contact with the sample emitting different radiation produces signals. These signals or the radiations can be used to monitor the sample characteristics. Characteristics of the surface like composition, stoichiometry, and elemental distribution or elemental mapping, etc. How the different elements in a sample are distributed, whether they are uniform or they are not. Electron beam scans in a pattern called the raster scan pattern, which is also known as rectangular pattern of capturing an image and reconstructing on a screen. The position of beam is combined with the detected signal to produce an image. In your mind, there must be coming, what is a raster scan pattern? A raster scan or raster scanning is the rectangular pattern of image capture and reconstruction in television. The term is used for raster graphics, the pattern of image storage and transmission used in most computer bitmap image systems. The word raster comes from the Latin word rastrum or a rake. The pattern left by the lines of a rake when drawn straight resembles the parallel lines of a raster. This line by line scanning is what creates a raster. It is a systematic process of covering the area progressively, one line at a time. To discuss the X-ray detector or the device that detects X-rays in EDX measurement. As the name itself suggests, it is the detector for X-rays. This is used to measure the flux distribution of any object in space, spectrum, and other properties of X-rays. EDAX consists of three basic components, as it can easily be seen in the diagram, that must be designed to work together in order to achieve accurate results. The other part is the SDD, silicon drift detector sensor. Then preamplifier is used, and lastly the digital pulse processor is a schematic illustration of X-ray detector. As you see, there is a sensor that senses and passed on these results to preamplifier, and the preamplifier after amplification sends the results to processor. We will be studying each of them one by one in details. So here we begin. First component of X-ray detector is silicon drift detector, which is abbreviated as SDD. The characteristics of SDD are: it has high count rates, it has high energy of resolution, it is thermoelectric, it has small value of anode capacitance. The first is silicon drift detector, or commonly known as SDD. SDD consists of a large amount of fully reduced, the highly resistive silicon is used here, in which an electric field with a strong component parallel to the surface moves the electron generated by the absorption of ionizing radiation towards anode. The electric field is generated by the reverse biased electric field strips, thereby covering one surface of the device. The radiation entrance window on the opposite side is made by a non-structured shallow junction, giving a homogeneous sensitivity over the complete detector area. The front end transistor of the amplifying electronics is unified on the detector chip and is further connected to the collecting anode by a short metal strip in order to utilize the small output capacitance. As the voltage is applied at front and rear side of the whole device, it becomes depleted from charge carriers. When X-ray quanta hits the detector, charge clouds of the electron pairs are generated. They are separated under the electric field. The positive charge holes travel towards the electrode and the electrons are floated along the potential valley towards the anode. This way, signals are generated and plotted with time. Silicon drift detector measures the energy of an incoming photon by the amount of ionization it produces in the detector material. In the SDD, the material used is high purity silicon with a very low leakage current. The high purity allows for the use of Peltier cooling instead of traditional liquid nitrogen. The major distinguishing feature of a SDD is the transversal field generated by a series of ring electrodes that causes charge carrier to drift to a small collection electrode. The drift concept of SDD allows significantly higher count rates coupled with a very low capacitance of the detector. In older detector designs, the collection electrode is centrally located with an external FET, the field effect transistor. The external FET to convert the current into a voltage and thus represents the first stage of amplification. Newer designs integrate the FET directly into the chip, which greatly improves the energy resolution and throughput. This improvement is due to the reduction of capacitance between anode and FET, which reduces electronic noise. Is the schematic illustration of silicon drift detector, the SDD. You can see the above diagram along with the numbering which is used for labeling. Number 1 is collimator. The collimator provides a limiting aperture through which X-rays must pass to reach the detector. Number 2, the electron trap. Electrons that penetrate the detector cause background artifacts and also overload the measurement chain. The electron trap is a permanent magnet assembly that strongly deflects any passing electrons. The third point is window. The window provides a barrier to maintain vacuum within the detector while being as a transparent to as possible as low energy X-rays. The fourth is sensor. Sensor is a semiconductor device that through the process of ionization converts an X-ray of a particular energy into an electric charge of proportional size. Two main types of sensors are used for X-ray detection, that is traditional silicon crystals drifted with lithium, so called SiLu, and newer faster silicon drift detectors SDD, which have largely replaced them. The FET or field effect transistor is connected directly to the sensor. The sixth, detector cooling SDD detectors operate a few tenths of degree below zero and are cooled by Peltier device. Peltier device is a thermoelectric device bound to the SDD sensor. Heat from these devices is transferred to cooling fins in the body of the detector. It is by a cold finger or heat pipe where it is dissipated. Next, after SDD, we will discuss the preamplifier. It is again an electronic device that amplifies a weak signal into an output signal. The input signal must be noise tolerant and strong enough for further processing. Preamplifier is always close to signals in order to reduce the effects of noise and interference. An ideal preamplifier will always have the following characteristics. There should be constant gain through its operating range. It should have high input impedance and low output impedance. It should be able to boost the signal strength in order to derive the cable to the main instrument without degrading signal to noise ratio. Now we will discuss the another component, that is pulse processor. The voltage signals that are formed are passed to a pulse processor, which measures the signals and then further passes them on to an analyzer for the display of data. The pulse processor discriminates the energies of the incoming X-rays and between X-rays that arrive in the detector. So this is an important component, and this part of process is very important because the discrimination of X-rays is very important here. The whole mechanism of this detection is based on this discrimination of X-rays. The time spent in averaging the signal, or we can say in removing the noise from the data, can be varied by adjusting the process time. As the count rate increases, the pulse processor is not able to distinguish between the two incoming X-rays. As a result of it, both are rejected. As count rate increases, dead time also increases, and if the dead time increases to 100%, at that time no X-ray will be processed and no data will be collected. The signal or the voltage step from the preamplifier is transformed into a voltage pulse that is suitable for the multi-channel analyzer. The time over which the waveform is averaged is called the process time, or we write it TP. TP is under control of the operator. The longer the TP, the lower the noise, but more time is spent measuring each X-ray and the fewer events that can be measured. If noise time is minimized, the resolution of peak displayed in the spectrum is improved and it becomes easier to separate or resolve. Last comes the analyzer or the computer display. It is the last component of the energy dispersive X-ray analysis instrument, and is clear from the name itself that it displays the final result. It receives the output from the pulse processor and it displays it as a histogram of intensity versus voltage. The voltage range is displayed on x-axis, which is divided into various channels. Each channel corresponds to a given energy range like 0 to 30 kiloelectron volt for SEM or 0 to 40 or 0 to 80 kiloelectron volt for TEM, and is assigned with a fixed number of X-rays containing relevant energy, and the results are displayed as a histogram of intensity versus energy. There are other components of EDX that plays an important role in the working of EDAX. Number one is the collimator assembly. The function of collimator is to provide a limiting aperture through which X-rays must pass to reach the detector. This ensures that only X-rays from the area being excited by the electron beam are detected. The second component is electron trap. Electron trap, the electrons, those penetrate the detector, cause background artifact. The electron trap is a pair of permanent magnets that strongly deflect any passing electrons that could cause background artifacts. The third is window. The window provides a barrier to maintain vacuum within the detector whilst being as transparent as possible to low energy X-rays. A polymer based thin window is used that can transmit X-rays from elements heavier than beryllium. The material used for the crystal is silicon. When an incident X-ray strikes the detector crystal, its energy is absorbed by a series of ionizations within the semiconductor to create a number of electron hole pairs. An electron hole pair is created for every 3.76 electron volt of incoming X radiation. Thus, for example, a nickel K alpha X-ray photon 7471 electron volt will produce a current of 1966 electrons. The electrons are raised into the conduction band of the semiconductor and are free to move within the crystal lattice. When an electron is raised into the conduction band, it leaves behind a hole which behaves like a free positive charge within the crystal. A high bias voltage applied between electrical contacts on the front face and back of the crystal then sweeps the electrons and holes to these opposite electrodes, producing a charge signal, the size of which is directly proportional to the energy of the incident X-rays. Component is the FET, the field effect transistor. It is the first stage of the amplification process that measures the charge liberated in the crystal by an incident X-ray and converts it to a voltage output. During operation, charge is built up on the feedback capacitor. The sharp steps on the voltage buildup are due to the charge created by each X-ray event. The voltage step size is proportional to the incident X-ray energy. This accumulating charge has to be periodically restored to prevent saturation of the preamplifier. The sixth component is cryostat. The charge signals generated by the detector are small and can only be separated from the electronic noise of the detector. If the noise is reduced by cooling the crystal and FET, the noise determines the resolution of a detector, particularly at low energies. The EDS detector is cooled using a reservoir of liquid nitrogen held in a DVAR. The vacuum is maintained at low enough level to prevent the condensation of molecules on the crystal. Now we will discuss the application of EDX in scanning electron microscopic systems. Energy dispersive X-ray spectroscopy, EDS or EDX, is a chemical microanalysis technique used in conjunction with scanning electron microscope or SEM. The EDS technique detects X-rays emitted from the sample during bombardment by an electron beam to characterize the elemental composition of the analyzed volume. Features or phases as small as 1 micrometer or less can be analyzed. When the sample is bombarded by the SEM's electron beam, electrons are ejected from the atoms comprising the sample surface. The resulting electron vacancies are filled up by electrons from a higher state, and an X-ray is emitted to balance the energy difference between the two electron states. The X-ray energy is characteristics of the element from which it is emitted. The EDS X-ray detector measures the relative abundance of emitted X-ray versus their energy. The detector is typically a lithium drift silicon solid-state device. When an incident X-ray strikes the detector, it creates a charge pulse that is proportional to the energy of the X-ray. The charge pulse is converted to a voltage pulse, which remains proportional to the X-ray energy. It is converted to the voltage pulse by a charge-sensitive preamplifier. The signal is then sent to a multi-channel analyzer where the pulses are sorted by voltage. The energy as determined from the voltage measurement for each incident X-ray is sent to a computer for display and further evaluation of the data. The spectrum of X-ray energy versus counts is evaluated to determine the elemental composition of the sampled volume. Now, let's summarize this module, or what are the elements we have studied in this module. The major component of EDX are the excitation source, which is also known as electron beam or X-ray beam, the X-ray detector, the pulse generator, and the analyzer. Electron beam excitation is used in SEM and STEM also. X-ray beam excitation is used in XRF spectrophotometers as well. A detector is used to convert X-ray energy into voltage signals. This information is sent to a pulse generator, pulse processor, which measures the signal and passes them onto an analyzer for data display and subsequent analysis. The most common detector now is silicon lithium detector, cooled to cryogenic temperatures with liquid nitrogen. However, newer systems are often equipped with SDD with Peltier cooling systems. Thanking you.